Great. Good evening. My name's Josh Watzman. I'm a software engineer at Facebook. I'm going to be talking about Facebook's dialect of PHP called Hack. In particular, I'm going to be talking about the Typechecker for the Hack language, which is written in OCaml, and how we parallelized the Hack Typechecker without language level support for parallelism in OCaml. So I'm going to give a very, very brief introduction to the Hack language, just to sort of ground what I'm talking about. This is not a Hack talk or a PHP talk, don't worry. Then I'm going to talk about how we did multi-threading for the Hack Typechecker, and then how we did the incremental update mode that the Hack Typechecker has. And the combination of the multi-threading and the incremental updates is what let us deploy Hack at Facebook with a 100 millisecond response time for type checking, approximately. So to sort of ground what I'm talking about, here's a brief introduction to the Hack language. Hack is a dialect of PHP developed at Facebook, like I said. The most important feature of Hack is that it is gradually typed. It has a type system and therefore needs a type checker. It's gradually typed, meaning that we require type annotations to be written at function boundaries. Functions need to have their arguments or their parameters type annotated, as well as their return types. And the type checker uses those in order to do inference locally in the function bodies. If an annotation is missing at a function boundary like that, we do not try and infer it. We just assume the programmer knows what they're doing and let the type unify with anything. So there's no global inference going on, and that becomes important for how some of the, it makes a lot of the multi-core stuff tractable. I'll get to that in a minute. It's been deployed on Facebook.com for a few years now, and it runs Facebook, tens of millions of lines of code running. The scale of that is also important for why the incremental updates and why the multi-core support is important. A few other things about the language. It has a really terrible name. I'm very sorry about that. It's ungoogleable. Hacklang.org is the website if you want to see it. The type checker, as well as the runtime, are all open source. It's under the HHVM project, which is Facebook's runtime for PHP and Hack. I'm not going to talk about HHVM today, but the Hack type checker is part of that project. So the only slide in this talk with PHP on it, this is what some PHP looks like on the left. This is an increment function. It returns the value +1, and then the function f, if you invoke it, calls increment, would echo 42 plus 1 is 43, and so it would echo 43. This does what you expect. On the right is the equivalent Hack code. It looks a lot like the PHP on the left. It's explicitly annotated that my increment function takes an integer and returns an integer, as you would expect. That was clearly the intent on the left. And then the function f doesn't return a value, and so like in the C parlance, it returns void. The type checker is able to take these annotations and see, yes, the increment function, you're allowed to add 1 to an integer, that's still an integer, and does all the local inference to make sure that's valid, but does require the type annotations at function boundaries in order to do that inference. Otherwise, it would just give up and say, I guess you know what you're doing. So the Hack language, like I said, it runs Facebook.com. It's tens of millions of lines of code. And so in order to get the latency requirements that we wanted, we needed to do a bunch of clever things to the type checker. We needed to be parallel, and we needed to have incremental updates. The parallelism is important so that we can get up and running on those tens of millions of lines of code without waiting an hour and a half, which is approximately our single core startup time. And incremental updates are important so that we can get low latency once the type checker is up and running and you're doing your everyday coding. So multi-threading is where I'm going to start talking about. And in order to talk about how we multi-threaded the type checker and how that system fits together, I need to go into a little bit of detail on how the type checker type checks Hack. Again, the type checker is written in OCaml, but the language that's type checking is Hack. And so in order to talk about, one of the things we did was very carefully arrange the way we did type checking such that the multi-threading would be possible. And so I'll get to that in a second, but let me talk about how we actually arranged it in 5 phases. The details of what exactly these are doing aren't super important. The gist of it is that we start with parsing, which is reading files off of disk, building an AST. We then build something called the global environment that I'm just going to totally gloss over for this talk. We do something called naming, which is massaging that AST into a more useful format to do type checking on. PHP and Hack have a bunch of bizarre rules around scoping, and so that's one of the major things that's resolved during naming, as well as generally like figuring out the names of things and scoping and that sort of thing. An important phase that will come up over and over is called declaration, which is looking at all of the functions and classes and methods that exist and extracting their type signatures. So you have the declaration to say, I have a function f, it takes an integer and returns a float. Declaration is not concerned with the bodies of the functions. That happens during typing. Whenever we look at all of the bodies and say, okay, here's the body of f calls g, I'm going to look up the declaration for g, which was computed in phase 4 during declaration, and make sure that the arguments and the return types and so forth all make sense. So we arranged these phases so that everything could be multi-threaded. Because computers have lots of CPUs and code has lots of functions, wouldn't that be a really convenient unit of work to farm out to our CPUs? And like I said, bootstrapping this typechecker on tens of millions of lines of code would be pretty hopeless otherwise. And so the phases are arranged very carefully such that this is tractable on a function level. If you notice, for example, typing. Typing doesn't require any information from any other function that was computed during typing. It only requires information from declaration, naming, and parsing. And similarly, naming doesn't require any other function to be named before I can name a given function. It just requires everything to be parsed. And so we use these phases as synchronization points. We just farm out parsing to random functions to random processes. They don't have to synchronize with one another. All we have to do is wait for everything to be parsed, and then we get all the parsed trees back. And then we farm out naming. And we know everything's been parsed at this point, and so we can just farm out naming indiscriminately. There's no synchronization between the different threads in order to do naming. They just name whatever function they're given, and then it all comes back, and so on and so forth. And so arranging the phases like this makes the multi-core conceptually really nice, since you don't have to worry about synchronization within a given phase. You just farm it out, and whatever happens, happens, and you get your results back. So now that we had conceptually arranged our system such that it could be multi-threaded, we run into a huge problem, which is that OCaml doesn't really have great multi-threading support. For people that have used OCaml, they do have a threading abstraction, which is emphatically not what we want to use here. Let me make sure I say this correctly. I believe the threading in OCaml is concurrent but not parallel, meaning that it's still single-threaded. It's like single OS threaded. It's locked to one CPU. It's sort of interesting from a conceptual standpoint, but it doesn't help you scale to more than one CPU in your system. So that was a non-starter. OCaml is getting a feature called multi-core, which does something more akin to what we want to do. That isn't out yet, I don't think, and it definitely wasn't a thing 2 or 3 years ago when we were building this system. So that didn't exist. So you can't use threads. What can you do? Well, the next thing you can think of is, well, we could fork the process, right? You can have n processes, one for each CPU. And it turns out that mostly works, right? You have a bunch of forked processes doing work. But sharing data between them then gets to be interesting, right? If you have threads, everything's default shared. If you don't, then you have to have a mechanism for sharing data. How do you share data between processes? Well, you can use inter-process communication, IPC. You can open up a socket and have them talk to each other over the socket. You can say, here, this process, here is the AST you need to name, and it could say back, here is the named AST back to some sort of master process, et cetera, et cetera. You can imagine how this would work. We implemented this. It turns out you can use sockets for this. It was implementable. We did it. It works. But there's a bunch of annoying problems around it. The big one we actually ran into was memory usage. You end up duplicating a lot of data between a lot of your different workers. So for example, with superclasses and subclasses, you end up having the same superclass sort of copied into a bunch of threads. Like the named AST would end up everywhere, and just lots of duplicated data. It was also slow serializing everything back and forth across these sockets. So IPC between processes works, but is slow. And so, okay, what can you do beyond that? What can we do? We have no language level support for this. IPC doesn't work. What we do now, we came up with what we do now, is have this magic mMapped region. The mMap is a system call on Linux. For those of you who aren't familiar with it, you can pass a couple of flags to it called map shared and map anon. But the semantics aren't important. What it means is you tell the kernel, here is a magic region of memory, like give me a chunk of memory. When I fork my process, this memory is not copied like memory normally is during a fork. The same physical frames end up in everybody's address space. And so writes to this, just to this region, in one forked process is visible in all of the others. Just as it has the same shared semantics as threads, except it's one region that's shared and everything else is copied. This is really nice because we don't need all this IPC serialization. We can just write things directly into this shared region. And it sort of behaves like traditional threading does in that respect, but it avoids a lot of the thorny issues around, particularly the OCaml heap and OCaml garbage collector are not thread safe. But they don't have to be for this approach, because the OCaml heap and the OCaml, all of that OCaml structures, they're not part of this magic region. They are not shared between processes, and so OCaml is none the wiser as to what's happening. We just need some C code linked in to the OCaml FFI to manage this shared region. And so I've been talking about this shared region. What is it? It is a shared lockless hash table that is shared between all of the different forked processes. It stores all of this information that's computed during the phases, the ASTs and the declarations and all of those structures. Importantly, what's stored in here is immutable data. Once you write it in, you might delete it wholesale, but you're never going to just change part of it. Which is really nice. OCaml deals really nicely with immutable data structures. You avoid a lot of concurrency issues with immutable data structures and that stuff. The hash table itself is not immutable. The data that goes into it is. But again, shared lockless hash table. We're talking C code. We're talking lockless data structures, concurrent data structures. That leads to a lot of really nasty issues. C, seg faults, all sorts of things. You might think that this is a really difficult and nasty piece of code, and it's not a simple piece of code to manage it. But there's a bunch of nice invariants that I'm going to talk about that make doing this tractable. The first one, deletes. There is only ever one process that issues deletes into the hash table. That process, when it issues a delete, is the only process that is talking to the hash table at the time. There's no concurrent readers or writers when a delete is happening. A delete happens whenever we're doing an incremental mode update. Whenever we've detected that a file has changed, we've recomputed part of that file, we delete the old data out of the hash table and insert the new data. It actually happens the other way around, I'm sorry. We insert the new data and then delete the old data, which means we can sort of batch up deletes and just let the master process hang on to them and delete them at some time later in the future to avoid a whole host of really nasty concurrency issues around deletes. For anybody that's ever done lockless data structures, the delete case is always the really, really nasty one. And so we just said, we're not dealing with it at all, goodbye, only one thread ever does deletes, no concurrent access, and a whole host of issues just go away when you do this. But we can still have some other concurrency issues. There's not only deletes, they're the only things that are happening. Another invariant we have is that basically all of the data in a given slot is equivalent. Meaning that if you're trying to insert some data into one slot in one process, and another process is trying to read out of the same slot, it doesn't matter if the second process sees that data yet or not, or in what order this is visible, as long as the write happens eventually. If the reader doesn't get the data that it wants out of that slot, it's just going to go, oops, I guess no one's computed this yet, and go and recompute it itself. So if this happens a lot, if the reader doesn't see written data regularly, that becomes a serious performance issue, but it's not a correctness issue. And so we didn't have to worry too much about this case when data is being inserted and read into the same slot. As long as it atomically sees it either there or not, it doesn't matter when it sees it. For people that have really been paying attention, you might be wondering right now when this case even comes up at all. I made a big deal a minute ago about the phases and how you don't have to do any sort of synchronization between the phases. So when are you ever reading and writing, reading and writing into the same slot at once? I said that in order for naming to proceed, parsing had to have finished, and parsing is never going to read anything else, any other results of parsing. And this would imply that that's in fact happening. And it turns out that I glossed over one issue where we actually do need to synchronize within a given phase. And that has to do with declaration. Remember I said a minute ago, declaration is computing all of the function signatures. I'll take questions at the end. Declaration is computing all of the signatures of all of your functions, what their parameter types are, what their return types are. And it turns out for performance, we need to inline the declaration of superclasses into subclasses. If I know I have a foo, or in this case if I have a cat, and I want to call a generic function that might be on animal, every time I call that function, I don't want to have to traverse up cat's inheritance hierarchy to find that function. Facebook has some really nasty deep inheritance hierarchies that makes this slow. We shouldn't have those inheritance hierarchies, but it isn't the job of the hack team to try and mandate that on our front-end engineers. We can try and get them to fix it, but our system should work even in the presence of those. So we have to inline superclasses into subclasses, meaning that in order for declaration of cat to have finished, we needed to have finished declaring mammal, and for that we need to have finished declaring animal, and so on recursively. And so, the case I was talking about a minute ago, a read and write into the same slot can happen if we know cat is proceeding along, cat sees that mammal hasn't been declared yet, goes on and declares mammal, and cat has finished declaring mammal and is about to write mammal in, and then dog starts up, and dog may be trying to read the slot for mammal at the same time that cat is writing it. Dog may or may not see that. Like I said, dog may go off and recompute the same data that cat just computed. That would be too bad. It's a waste of CPU, but it would still work. Since all these functions are idempotent, the declarations are equivalent to one another if you keep recomputing them. Similarly, since we have equivalent data, if two people if cat and dog both compute mammal at the same time and both try and write it, one of them is safe to just completely drop on the floor arbitrarily. We don't care who wins this race. As long as one of the two gets in there, we don't care who it is, they're equivalent, and other threads can continue using whatever data ended up in there. One thing that's not obvious though, within a given process, if you write some data, that data needs to be visible for subsequent reads as soon as the write returns. If we have a racing write like this, it's not acceptable for one of the writes to return saying, oh, you lost the race, the data will be written eventually, and then a later read to fail and say the data's not there because the other writer hasn't actually finished yet. We didn't realize we needed this invariant, sorry, one step back. The reason we need this invariant is because if you're cat, and you're computing mammal, you expect to go compute mammal, write the computation for mammal into the hash table, go back to cat, and then be able to read out what you just computed for mammal and inline it into cat. And if that fails, you're going to miss a whole bunch of all of the fields that we expected to be there from mammal, you're going to miss them on cat. It turns out detecting this failure case where a declaration should be there but it isn't is rather difficult because of some complications around PHP compatibility that I won't go into. So we needed to guarantee at the hash table level that this always happened within a given thread. It's not hard to guarantee, but it just actually took us 6 months to realize we needed to guarantee it in the first place. And we had these really nasty issues where very occasionally one person would say, on my server, like I'm writing some code and it thinks these methods don't exist that I know exist. Classic concurrency issue. Really big pain in the butt to track down. My favorite part of this story, though, is once we finally fixed it, it involves a busy wait in one place. In order to make a busy wait less expensive, we have an asm volatile for an x86 instruction. And so our beautiful OCaml type checker that's like going along with types has at its core some C code with a single assembly instruction in it for performance reasons, which is great. So I'm talking about bootstrapping the type checker, getting it up and running in parallel, but one of the other major things that we need is the incremental mode. Since we have tens of millions of lines of code, at any given time, once you've got the type checker bootstrapped, you're probably changing about 5 of them, not tens of millions. And so we don't want to keep re-updating everything all of the time. Starting from scratch, we can get about a 3-minute startup time. We need 100 millisecond response time in order for developers to really accept what we're doing, that we're not getting into their workflow, their fast, typeless, compilerless workflow they're used to with PHP. And so we needed this incremental mode update, or this incremental mode. I'm not going to go into too many details about how it works. The gist of it is that you have a server running in the background that uses the Linux iNotify subsystem to watch for file system changes, update changes in real time. You can basically say, function f.p or file f.php changed. Let me reread everything that's in f.php. The function f changed. Let me recompute all the phases for f. However, if you have a function g and g calls f, we also need to track that dependency so that we go and recompute information for g, even if the file that g is in didn't change. If the signature for f changed, the calls from g into f might now be invalid. So we need to track dependencies. It turns out at a high level, tracking the dependencies between these functions is not that difficult because, again, the way the phases are laid out, during the 5th phase, typing the final phase, you're typing all of the bodies. In order to do that typing, you need to look up the declarations for other classes that were computed in the previous phase. Anytime you do a lookup, we write a dependency into a table saying, you did this lookup, you were type checking G, you called F, you looked at the declaration for F. We track that. Lots of edge cases and nastiness around it, but the gist of it is simple, meaning that we now can look up the reverse dependencies when a file changes, recheck everything, rerun all of the phases, and things work out really nicely. So that's all I've got. My conclusion is basically that parallelism and concurrency are fun, particularly when your language doesn't have support for them. And so you have to write your own bunch of C code, invent your own invariants, invent your own data structures. They're specialized to what you're doing, but nicely specialized such that we can get rid of a whole host of nasty issues and make something that's fast, that even works at the scale of Facebook's front end. Hacklang.org is the website for Hack. And if we have time, I'm happy to take some questions now, or I'll be around later. Yes?
So does OCaml provide primitives for doing atomic updates, or did you write those in your C layer?
It's all in C. As far as OCaml is concerned, the API we expose to OCaml is basically read this key out of the hash table.
So I guess the question is, could you implement this lockless hash table natively in OCaml if you wanted to?
I don't think OCaml exposes the right primitives, but don't quote me on that. For us, given that this is like inherently very imperative, gnarly code, we wanted to write it in C to make sure that we got the invariants right, given that we were working around deficiency in the language in the first place.
I was going to say, probably does, because it doesn't support multi-threading.
That would be my suspicion. I don't know if the new multi-core support might start providing those. I don't know either way on that. Yes?
So if you have two concurrent writes into this lockless hash table, for example, you're writing two strings. The way you do it, you put a string on a heap and then place a pointer to the string into the hash map, right? So if you are uploading the same data twice, you are putting two copies of a string onto a heap. Doesn't it cause a memory leak?
No. So because we're careful about this. You also want to be very careful what you mean by heap. You can't store any pointers in this data structure into the OCaml heap because those are not shared between the processes. And so any data that goes into this region has to be, the API is like, write this key and this value. That value is actually copied into the region. And the place that it's copied into is garbage collected. We have our own, it's a very simple bump allocator garbage collector. As simple as gets for this, but fine for our purposes since we are simple. So we eventually, if memory fills up, we know what things are in the hash table because we have the whole hash table, and we collect everything. So no, we're careful about it. Yes?
Sorry, I'm just being a troll. Why did you consider using Haskell?
So OCaml is nice for a lot of this is my personal opinion. The real reason is that a guy named Julian started the project and he decided to write it in OCaml. And I think he decided to do that because OCaml is what he knew, because he was like went to INRIA and like did all that and was steeped in the OCaml stuff. For me personally, it was really nice working on the system that most of our functions are pure. Whenever you work, like it's the high-level Typechecker, most of it's pure. But occasionally you just want a ref cell somewhere, and that's a really useful thing to be able to do. So I like OCaml for that reason, that you can have the impurity when you need it. I find laziness very difficult to reason about, and I think the performance of our Typechecker is, I won't say easy to reason about because it's a complicated system, but it's tractable. I don't even want to know where I would start if it were lazy. Reasonable people can disagree with me. That's my own personal, Vim Emacs holy war on OCaml Haskell. The real reason is because the guy who started it decided to use OCaml because that's what he knew. Yes?
You mentioned that there was some very specific semantics in PHP with respect to concurrency and hash tables. How closely did you want to ape the PHP semantics there?
Sorry, what do you mean by PHP? This is just type checking PHP. It's all static analysis of the PHP code. But I'm not sure if I understand your question.
Specific kind of PHP thing with respect to concurrency and hash tables? PHP doesn't really have very well-defined semantics for thread.
It has no semantics for it at all.
So what was that? You mentioned in passing that there was some detail of PHP.
Do you remember where it was exactly?
It was, if you go back to the slides, you just go back, it was there. So you said that there was, you realized that there was something specific about PHP that you can, I was intrigued by what that was because most of the semantics would be dynamic.
Yeah, it's all dynamic semantics. I'm trying to think. I was just talking that we need to inline all of the superclasses into the subclasses. I remember what it was. It's that I was talking about backwards compatibility with PHP, where a declaration can be missing and that was a legal state to be in. Is that what you're talking about?
Oh, right, yes.
Yes. We should maybe talk offline about it. It doesn't have to do with the dynamic semantics of PHP. It has to do with, for compatibility reasons, the Typechecker allows classes that you refer to in Hack to not exist. It assumes they exist in PHP files that haven't been converted that it can't see. And so it's a legal state for MAML to actually not be a part of the type system. Oops, I dropped the mic. So that's a legal state to be in, and so when we come to this invariant, it's difficult to detect when this is violated because it's legal for data to be missing. And yeah, I can talk in more detail offline if you'd like. If we have time, sure.
Yeah. You see little parentheses after your key names, and I think you mentioned if something isn't in the hash table, we'll go and so should we assume that these are really funcs where essentially the key determines the value? Or
I guess if you want to think about it that way, that's not wrong. The key would determine the value, but the keys are like hashes of what, but like it's a hash of like, this is the named AST of your function foo. But I guess in some sense you could think of it that way. We don't think of it that way in the implementation. We do really think of this as just a key value store. But the way it's used is, yeah, one process will go, oh, I need data that should be at this key. If it's not there, I'm going to go and recompute that data. And this only happens during declaration. It's a fairly bizarre thing. Most of the time you're just told, parse this file. And you know, the contents of this file are on disk here, and then please write the file into this key over here, the parse tree of the file over here. And you don't have to worry about data being there or not being there. You're just told, the worker's just told what to do and what to do. It's just these edge cases around inlining the superclasses during declaration because you need other data from declaration during declaration. And that's the only case where that comes up. Anything else? Sure.
So the picture of the dependency graph and the fact that we need to track dependencies, is the software that tracks dependencies also parallel?
The dependency tracking is, so yes, but it's done as part of the type checking, right? Like when I'm type checking, I just say, I'm type checking F, and F calls function G. And so in order to type check F, I need to look up the signature for G. The API inside the internal of the type checker that look up G, just record that dependency into a dependency table. That's another part of this shared lock list data structure. Another section of it is a dependency table that just stores these pairs. Yes?
Same problem with basically synchronizing with the file system. So if the file changes while you're already running the type checker, and I guess one of these processes already loaded basically the file, and then the file changed, and then the load process gets the state what it needs the file and then reads it. Then it doesn't actually compute the same.
Yes, there are some issues we have to be careful around that. It basically comes down to the Linux kernel gives us a bunch of iNotify events all at once, and then we run through all 5 phases of just those events and rereading those files. And if anything changes while we're doing that, they get queued up, and then we go around again with the next batch of events.
Consistent snapshot of the whole source.
Yes. If you manage, so let's say you change the same file twice in a row, and it erases such that we get the iNotify event, but then you change the file the second time before we process the first notify event and reparse it, we'll just end up reparsing the same file twice because we'll still loop around twice to make sure we got it. We'll just do the same work twice and not a big a deal.
We might as well take this on to the next group. So big round of applause for John.
Thanks.